Started. So welcome to our online series on understanding and exploring network epidemiology in the time of coronavirus. We're so thrilled at the phenomenal response we've had to this series, and we're excited to get started. I'm Michelle Gervin. I'm a professor of physics at the University of Maryland, and I'm director of the Combine program. Combine stands for Computation and Mathematics for Biological Networks, and it's one of the sponsors of this series, along with the Vermont Complex Systems Center. These are really difficult times we're facing. Our lives have been turned upside down in just a matter of weeks. Already, over 80,000 people have died because of COVID-19, and we really don't know how this is all going to end. As scientists, so many of us have been trying to understand the emerging work that has come out with data analysis and modeling efforts to help address this pandemic. Some of us are also trying to figure out how we might lend our own expertise to this effort. So that's where this series comes in. The goal of the series is to introduce concepts of network epidemiology and also highlight some current research on COVID-19 that uses network epidemiology, and get together to discuss various modeling approaches and data analysis approaches. So I keep saying network epidemiology. What's the difference between that and just epidemiology? Well, network science helps us think about how the pattern of connections in a system is important. And obviously, this is a key element in understanding how disease spread. We need to know, how does the pattern of social connections influence the spread of an epidemic? And by understanding the importance of these network structural features, we can help design better intervention strategies and understand, for example, how different types of social distancing might have different kinds of impacts. Our intended audience for this series is really broad. We have people from a lot of different fields here: life sciences, public health, social sciences, computational and computer science, physics and mathematics. In addition, our participants are drawn from a variety of career stages. We have graduate students, faculty members, postdocs, some undergraduates, and people from industry, government labs, and nonprofits. So we're thrilled to have you all with us today. Our series is divided into two parts. We have a weekly tutorial seminar series and a discussion series. So some of you have signed up for just the tutorial or seminar series. These will be hourly session, about an hour every week, and the schedule is posted here. So today we have a tutorial, which is an intro to network epidemiology. Next week, we have another tutorial which focuses more on the data analysis side of things, including visualization, and that's by YY On from Indiana University. The following week, we have Sam Scarpino from Northeastern University. And actually, I can announce the speaker for week 4, who is Ginestra Bianconi from London. Oh, I'm forgetting, I'm blanking on which university. Queen Mary College of London, I think that's the right name. All right, and so we also have the discussion series. Many of you are also here for the discussion series, which will have a session immediately following each tutorial seminar. That's a separate Zoom link, and that'll start after the first session. And for this, we have participants, we'll have a method for participants to organize into small groups, and these small discussion groups will meet between weekly sessions. I'll give you more details about that in the discussion series session to follow this one. An important note here, Due to the wonderful, overwhelming interest, there are no spots remaining in either the seminar series or the discussion series, so please don't share those Zoom links with others. However, there are other ways to be involved and stay connected. So we'll be posting videos of tutorials and seminars on our YouTube channel, and you can get to there from our short link go.umd.edu/net-covid-videos, net-covid-videos. And you can also follow us from our event website, which you can reach from the combined website or directly at go.umd.edu/net-covid. NetCovid is sort of our tagline. In fact, it's our hashtag. If you want to follow us on Twitter, #net_COVID, or you can follow Juniper Lovato, who is one of our co-organizers from the University of Vermont. Oops. All right. So I want to remind you that we'll have questions. We'll take questions in the chat window. We encourage you to ask questions, especially at the end of the presentation. We have a number of co-hosts who will be acting as facilitators to monitor the chat and bring up your questions to the speaker. And as I said earlier, we tried to work out a lot of the technical issues for this. Hosting a big group can be a little bit complicated. So bear with us if we have any technical difficulties. And so with that, I really would like to introduce our first speaker, whom we're so delighted to have. Laurent Hebert-Dufresne is an assistant professor at the University of Vermont in the computer science department. He's also part of the Center for Complex Systems there. He received both his bachelor's and his PhD in physics from the Université Laval in Quebec. Prior to joining the faculty at UVM, Laurent was a James S. McDonnell Fellow at the Santa Fe Institute. His research focuses on the intersection between network theory and nonlinear dynamics. So both of these are really important for understanding the spread of disease. And he's had a number of great papers specifically on network epidemiology, so we're delighted to have him here today. So with that, I'm going to stop sharing my screen and turn it over to Laurent.
Hello, the screen sharing is currently disabled for me.
Oh, I think one of us, it might have to be Glynis at this point. Yeah, so Glynis should have the hosting privileges. Can allow you to
I'm going to do that, hold on. Spotlight video, but also...
I'll set up a timer while you do that. I should warn you all, I'm definitely going to go over time, but at least with a timer, I'll be sure.
Yeah, we took a little while getting started.
Sorry, you should be able to do so.
Host disabled participant screen sharing.
Michelle, you're currently the host, so I think you're the one that has all the major privileges.
I don't have the, let me try again. Okay, I'm gonna make you the host then.
Okay, I got it.
Okay.
Oh, you have it now?
Yes.
Oh, okay, well then
Can you see my screen?
No.
No. All right, I'm making you the host. You're the host now. Yes.
We're good?
We're good.
Okay, thank you. Okay, so I'm starting my timer. Like I said, I'll definitely go over time, but I think it's going to be worth it. Also, I just saw that Michelle said that this would be recorded and posted on YouTube. So we'll all be able to rewatch this tutorial in the future. That also means that my mom will be able to watch it. So I thought I'd just explain why I'm wearing a hoodie and I'm not shaved while talking to 200 people. So this is being filmed in April during the quarantine. And it's also the hockey playoffs, or it would have been the hockey playoffs right now. As you all know, Canadians don't shave during hockey playoffs. So that's the setup. Otherwise, everyone else, welcome to my living room. I'm very excited to be here today. Normally, I'm at the Vermont Complex Systems Center at the University of Vermont. I'm an assistant professor of computer science. But I think what we're doing today is really important. I know we're all quarantined, and I think this event can help us all in a lot of different ways. So network epidemiology right now is at a point where we can definitely help more classic epidemiologists think about the structure of their systems. We're also at a point where we need fresh ideas and new blood to join our community. I also think it's important to think about the relationship between different models, because we keep being flooded with different forecasts, hundreds of different forecasts a day. So it's important to be well-versed into modeling to be able to understand the assumptions and mechanisms behind everything. So I want to thank you all for being here, and the University of Maryland and the NSF combined program for bringing us together. So I've been working in network epidemiology for over a decade now, and today what I'd really like to do is share some of the big picture lessons that I've learned during that decade. So as you see on the screen right now, I think one key thing to remember throughout the talk is that a model is not better because it is a network model. Network models are not somehow different from every other type of disease models. They're just more general because they consider a large array of potential structures and not like specific ones like classic epidemiological models. So what that means is that because they're more general, to use them in practice, it requires more data and or assumptions. So they're harder to use, and I like to remember often what an old friend always says, which is that we want our models to contain everything that we do know and nothing that we don't. So network models have the potential to be more informative, but they're so hard to work with that we have to be very careful and well aware of their assumptions and underlying mechanisms. The key part of why they're still interesting, despite being hard to use, is that they can allow us to consider, as Michelle said in introduction, the heterogeneity of contact structure and of the population in which a disease might spread. They also allow us to think about randomness, which is a very hard thing to do in most modeling. And lastly, as we'll see throughout a few examples, they can be useful both for modeling specific interventions and thinking of the possible futures of an outbreak, but also for specific forecast. As a lot of people are trying to do now, trying to determine when the COVID outbreak might peak and start decreasing. So this is the outline for the talk. I chose to go really deep in details. I'll have a lot of references throughout so that you can refer to specific textbooks and or paper, but I really want to cover the whole array of network epidemiology. Since this is going to be on YouTube, I think it's useful also to have a specific outline. Maybe the organizers are going to be able to tag different items so that people watching this in the future can jump to specific sections. If you're watching this on YouTube in the future and that's not available, then I'm sorry for giving more work to the organizers. All right, so classic models, right? I think we've all seen these models in the news and in the literature recently. So I'll go over them quickly, but it's important to understand their basic assumptions because we're going to keep that fixed throughout the talk and really play with structure and not so much the underlying epidemiology of network models. So we're going to be using two standard models, the SIR for susceptible, infectious, and recovered model, and the SIS model for susceptible and infectious. The key difference here is that it depends on whether you want to assume that the disease comes with some long-lasting immunity. So that's SIR, where the recovered individuals are either recovered and immune or dead, but regardless, they can get infected again. Or in a disease without immunity, where as soon as you recover, you might be infected again. We're going to keep those two models throughout the talk and play with their structure. You have like little cartoon of what these models might look like in practice. They both have this exponential spread in time. The key part is that SIR will eventually run out of susceptible individual to infect, peak, and decrease, whereas the SIS model is just going to reach a steady state, a level of equilibrium where there's just as many infections as recovery and level off to an endemic level in the population. So you've probably seen some animations of these classic models. So this is an SIR model that was simulated by the Washington Post You'll have the reference on the next slide, but you have little individuals that are little balls bumping around, bumping into each other. When an infectious individual, which is orange here, bumps into a susceptible individuals, which were the originally blue or greenish individuals, they just transmit the disease. And eventually, at a given rate, people recover and become pink. Once the entire population is pink, nothing can happen anymore, and you just run a new simulations to try and track the spread of the disease. And those are the classic models, right? So you could look at this and figure out that on average, every 4 seconds, an infectious ball bumps into 2 other balls. So one patient 0 turns into 2 4 seconds later. Those 2 individuals turn to 4 another 4 seconds later, and those 4 turn into 8, and you get this exponential spread of the disease. Those are the classic models. They can be analyzed very easily because there's no underlying structure. You have this mass action mechanism, which means that any potential interaction can occur. They're all equally likely. So they're pretty easy to model with mathematical formulas. So basically, here's how we would do it and how it's done. Classically in the literature, we would assume a population of n individuals, all possibly connected. We're not saying that all connections exist. We're just saying that they're all possible. And we're going to assume that infectious individuals transmit at a fixed rate. So if I'm infectious and I have a susceptible, healthy neighbor at a given rate, which might be once a day. So on average, it will take me 1 day to transmit the disease. I'll infect them. And I'm also going to recover at a fixed rate, which is going to be alpha. I'm going to keep those 2 rates fixed throughout the presentation. And then we can simply follow the number of infectious individuals through time. So I'm going to assume that everyone has seen a little bit of calculus before. If you haven't, this d over dt times I is just the derivative or the speed at which this number of infectious individuals is changing. So if you know your parameters and you know where you are, you can calculate this derivative, and it's telling you at what speed and where you're going. And basically, we're going to assume that this number of infectious individuals is going to go up with this term beta I, beta times S times I, and it's going to go down with this term alpha I. So what this means is that SI is a product that gives me the pair of all potential connections, all the potential connections between pair of susceptible and infectious individuals, and they transmit at a rate beta. Whereas alpha times I is simply the rate at which each infectious individual will recover. And really, because here I'm using an SIS framework to make it easier, I can say that, well, S is simply equal to N minus I because you're either susceptible or infectious. So even though it might look like there's 2 degrees of freedom, 2 variables, S and I in the system, because I know the fixed population, there's only 1 degree of freedom, 1 variable of interest, and it's this number of infectious individual. So I'm going to do a little bit of math so that we really understand where I think all of the intuition and all of the foundations for modern disease modeling come from, right? So we can look, we have this logistic growth of the epidemic, right? So we have beta times I, right? Initially, beta times I times N when I is very small, so that gives me an exponential increase. But because of this N minus I term, eventually I'm gonna peak when I can't infect any more individuals. So I reach a carrying capacity. So it's a classical logistic growth. And we can ask, what is the momentum caused by every single infectious individual early in the outbreak? So I'm going to take I dot, the derivative of I. I'm using a physics notation here for the derivative. I dot over I gives me the number of infections caused by every single infectious individual. And I'm going to take the limit of that when I is very small. And that gives me this relationship at the end, which is simply beta n's minus alpha. So that's what the number of infection or infection force caused by every early case. And basically, if this number is positive, so if beta n is greater than alpha, I'm going to grow. The disease is going to grow, right? It's going to spread further and further. So what we find is that there's an epidemic threshold such that if beta is smaller than this beta c determined by beta c times n equal to alpha, then this beta n minus alpha term is going to be negative and the disease will shrink. So there's a regime where the disease shrink and doesn't exist, can spread basically. And there's another regime above beta C where it can spread as much as it wants. And often you'll see this parameterized by this R naught quantity, which really is the average number of secondary cases that I will cause if I get infected early on, right? How many infections will I cause? And I tend to call that secondary infections. So this R naught here would be beta n over alpha. If it's greater than 1, I grow with this exponential rate of R naught. If it's smaller than 1, I decrease. And in fact, we can even ask if it is growing? Where is it going? How big is this outbreak going to get? And because I'm using SIS here, it's pretty simple. I can just ask, when is I dot, this derivative of I, going to reach a steady state? So stop moving, be equal to 0. And I can solve that equation. I get 1 minus 1 over R naught. So if R naught is infinite, everyone gets sick and stays sick. If R naught is around 1, then I get a tiny outbreak. Below 1, this doesn't even make sense, right? So below 1, there's just nothing going on, no outbreak. So that's like the classic intuition that we get from the standard SIS model. SIR model are similar, but as we'll see, they're a little different. But in terms of having this epidemic threshold, it's the same thing. So here I complete my picture of compartmental epidemiological models. I just add this idea that beyond the exponential rate, we know that if we look at varying the transmission rate, there's a regime on the left of my final plots here where there's just no outbreak. And there's a regime of growing outbreaks with growing transmission rate on the right side. So the same thing happens in the SR model. It's a little harder to solve. The classic solution comes from the 1920s, actually, by Kermack and McKendrick. You have the reference here at the bottom. It's a little more complicated because it's a transcendent equation. It's harder to solve, but it gives you the same behavior. There's an epidemic threshold at R naught equal 1, and then growing epidemics when R naught gets bigger and bigger from there. And that's, still to this day, that's the solution that a lot of people are going to use early on. That's why there's a big focus on R naught. So early in an outbreak, you really want to know what is the R naught of this disease. And I should stress already that R naught is both a property of the pathogen and of the population. Here we made a bunch of assumptions about the structure of that population, and we try to estimate those and use this formula to try and see how big this outbreak might get. Now, we still use this even though there's a lot of assumptions behind it, because often that's the best we can do with data available early on, but we'll try and relax some of those assumptions. So we're not going to play with epidemiological assumptions here. We're going to keep classic SIR and classic SIS dynamics. We're going to consider close population throughout the seminar, and we're also going to assume that all individuals are equally susceptible. In epidemiology, there's a lot of models that address these different assumptions, relax them, and make things more general. We're not going to go there. What we're really going to look at is how to play with structural assumptions. So the fact that here we're assuming that the contacts occur according to the law of mass action. All contacts are equally likely. And we're also going to look at the fact that here we're assuming a deterministic analysis, which means that we think the population is large enough so that I can use an ODE, a differential equation, which fixes my future, right? If I say where I am and what my parameters are, I get a number out of it. And that's a deterministic analysis. We know real diseases are really stochastic, random, so we're gonna have to relax that later on. And network science helps us do that. So we're gonna start with the first one here, this assumption of the law of mass action, right? We wanna move somewhere else. We wanna do our SIS model on something like a network. Where we know some individuals are going to have more connection, some individuals are going to be more central. And really what this means is that we need to consider links around individuals. So if I'm healthy right now and all my friends are healthy, I'm not going to get infected in the next instant, right? So if I know who's at the end of all of my contacts and what their status are, then I can have a better picture of whether I'm going to get infected in the future or not. The simplest way to do that is with pair approximations. So in the previous model, we were just distinguishing individuals. Are you sick or are you healthy, right? Are you susceptible or infectious? Here we're gonna keep doing that for individuals, but we're also gonna look at contacts, at pairs of individuals. So contacts can be of 3 types in the classic SIS model. You can have 2 susceptible individuals, we're gonna call it SS edge, or you can have an SI edge, which is the same as an IS edge, or you can have an II edge, right? And if we follow these types of contacts, then we can do a better job at tracking the disease in something like a network, because we have some approximation of a network structure through these pairs. And here I'm writing what these equations might look like. The problem already is that if I want to follow the evolution of SS pairs, I'm going to be thinking about triplets, about SSI triplets of nodes. To illustrate that, let's look at this little network here. Triplets wouldn't be a problem if we knew the network would be fully random, if we knew that every edge occurs with a fixed probability. In fact, if we make that assumption, so classic Hilbert graph, we would just go back to the mass action model. So we don't want to do that. We want to consider something more networky, where not all edges occur with the same probability. The problem then is that if you look, for example, at the ISI triplet in the middle of my little cartoon here, well, you'll see that if the first infectious node infects the middle susceptible node, I have one SS edge that turns to IS and one SI edge that turns to II. So triplets affect the future of contacts, even if nothing happens on those contacts. And then what we need to do is either embrace that complexity and start tracking triplets where we'll need to follow quadruplets of node and it gets untractable eventually, or we try and approximate what we don't know with what we do know. And often that's called moment closures in the literature. So I'm going to show you how a typical moment closure works. This is probably going to be the hardest mathematical part to follow for a while, but I think it's valuable. So we're going to zoom in on this ISI triplet that I was talking about. We're going to ignore the rest of the network for now. We want to know how can we approximate how many ISI triplets we have in the network. Well, ISI triplets are at least going to be proportional to the number of SI edge, that first edge in the triplet, right? So I can start with that. And then they're also going to be proportional to how many edges go out of that one contact. And here, I could say that, well, maybe that number of edge going out is the average degree, the average number of contact in my network. Maybe it's the average degree minus 1, because I already took an edge out of this green node. We don't know yet. We're just going to leave it as average excess degree. So for other edges coming out of the node. And then we're going to want to know, out of all those edges coming out of that node, how many are susceptible infectious, lead to an infectious node. So that's going to be proportional to how many SI edge I have in my network. But I need to make it a probability. What is the probability that my excess degrees are leading to SI edges or to I nodes? So I just need to normalize by all edge coming out of green nodes right now. And that's number of susceptible individuals times the average degree, right? So it's a little hard to follow, but it allows us to make steps in the network and introduce these two key quantities, the average degree and the average excess degree. We might be tempted to say that they're the same or that they differ by 1, but that would be a mistake. And actually, that leads to sort of the first network epiphany that I hope you'll all have today, if you're not familiar with this already, is that you don't want to assume any relationship between the average excess degree and the average degree of your network. And that's related to what often people will call the friendship paradox. So the friendship paradox is this idea that your friends have more friends than you do. And I know, some people might be thinking, I have some friends that have literally no other friends than me. That's fine. This is a statistical statement that is true on average. I'm sure those friends are great, but on average, most of your friends should have more friends than you do. And why is that? Well, imagine that you know the actual degree distribution, the number of friends per person in a population. Well, you're just a random person that's drawn from that distribution, which we're going to call PK throughout the seminar. Your friends, though, they're random neighbors. They're not random friends. So they're drawn proportionally to how many friends they have. Which means that they're not drawn from PK, they're drawn to K times PK, because someone with 10 friends is 10 times more likely to be a friend, to be your friend, than someone drawn at random. So just this basic statistical idea tells you that the average excess degree doesn't come from the same distribution as the average degree, and therefore you don't really know their relationship. And if you ignore the fact that they're not the same and that there's an interesting relationship between them, you just fall back on the mass action model again, right? So that's one key feature of networks, is that there's a difference between picking a node at random and following an edge at random. So if you know how to do those moment closures, you can specify a pair approximation model, and that's great because that's the simplest way to get out of this mass action formalism. Here we're transforming this one assumption into two assumptions. One is that we're going to say that contacts follow a distribution that is approximated by this metric for heterogeneity, average excess degree over average degree. And we're also making the assumption, and you might have not noticed it, but that the infection status is not correlated with contacts K, right? Obviously, the average degree of infectious individual is probably higher than the average degree of susceptible individual. They got the disease from someone, right? So when we were using those static numbers to describe the degree distribution, we were making this sixth assumption here, and we're going to try and relax that later. But the pair approximation is really, really fun because in the SIS case, it's only 3 equations. It's not much more complicated than the classic models, and it allows you to consider some heterogeneity and go much further, right? Here's a cartoon of why I keep saying heterogeneity and why that matters. So I wrote down very quickly the equation, the differential equation for this number of contacts SI, and it had 2 terms that were important and sort of fighting each other. One was that if you do transmit over an SI edge, you turn that edge into an II, and the number of SI edges go down, right? But it also increases with beta times this number of triplet SSI, because if I infect a neighbor and they have a lot of susceptible neighbors, I'm creating a lot of SI edges. And going over these edges, that's the term that's proportional to this average excess degree where heterogeneity is important. So if we go back, let's assume that this is a Poisson distribution on the left, and then this is the classic SIS or SIR picture on the right. So epidemic size is a function of transmission rate. If I start making my degree distribution a little more heterogeneous, and here I'm coloring, low degree as blue because those people are mostly safe. If you have only 1 contact or 0 contact, you're less likely to get the disease. Whereas high degree nodes are colored as red, or the high degree end of my distribution is colored as red because this is where the disease is gonna be, right? So I'm making it more heterogeneous. And if you're following what's happening to this epidemic size picture here, really what's happening is that as I make my thing more heterogeneous, I decrease my epidemic threshold, because it's very easy, even for a weak disease, to find the highly connected nodes, which we're going to call hubs, and start spreading from there. Right? So I'm decreasing the epidemic threshold, but I'm also decreasing the epidemic size for very large transmission rate. And that's because I'm having a lot of nodes that are hard to reach and that are going to survive for a lot longer. And that's an interesting trade-off that comes with heterogeneity. In fact, we're going to see another model a little later where if we push that to the extreme, so for very, very heterogeneous degree distribution, like power law degree distribution with small scale exponents, this average excess degree can be infinite, right? So your friend on average have infinitely many friends. What this means is that the epidemic threshold is just going to go to 0. Any disease will be strong enough to survive. And that might be kind of crazy to think, like, in what kind of population is the average number of friend of a person fixed, constant, but the average number of friend of friends is infinite? Well, we tend to have a lot of very heterogeneous distribution. That's a little like saying, if I pick a bank account at random, probably has a few $1,000s, right? If I pick a bank account at random while following a business transaction, I'm probably like in Jeff Bezos or Bill Gates' bank account, and then it's infinitely more money, right? So that's sort of the idea between following an edge and picking a node at random, and it's so important to disease transmission. The importance of behavior is really key here, and that's something you can't really put in mass action model, or you have to put it externally, sort of ad hoc, by changing your transmission rate. But there's this whole literature that, at least for me, goes back to 2006 with a great paper by Philo Gross in Physical Review Letters called Epidemic Dynamics on Adaptive Network. It really inspired a lot of my work. So there's a paper from 2016 by some colleagues and I that looked at something similar. And the idea is that with these basic pairwise models, just because we follow contacts, we can follow dynamics that doesn't involve the disease, but just involves contacts, the network structure. My classic example is always, you go to the grocery store, you're creating a contact with the butcher who's going to prepare your steak. But if you see the butcher sneezing on the steak, you can choose to rewire that contact from an SI edge to a SS edge. And that doesn't affect my epidemic status right now, but it affects my number of contacts and their type. So in that last paper in 2015, we looked at something that I think is really relevant right now with COVID. So we looked at this idea that this rewiring mechanism doesn't only occur around healthy people, right? So let's say that a nurse is caring for some patient. The nurse gets the disease from a patient. So the orange node here are infectious. Now, if the nurse is sick, he or she is probably going to stay home, and someone else, a substitute, is going to be brought in to care for the patient. Well, that means 2 things. That means that you're really helping the healthy patient that might be at the hospital for something else than the disease. They're not going to be in contact with a sick healthcare worker. But you're putting this new substitute nurse at risk because they're going to be in contact with the original sick patient. It's a little same thing that happens in classroom, right? My sister teaches elementary school. If she gets sick, it's pretty much sure that it's because of the kids, right? Kids are kids, they do what they want to do. And if she's sick during the school year, it's probably because of them. But if she stays home and the substitute is brought in without being told what's up, that he or she's probably at a risky, in a risky classroom, then they're put at a high risk. So we did this simple model. I'm just showing the equation in part to show you that it's not that much more different from what we've already seen. But this is an adaptive network model where we have this new rate, gamma, that governs this rewiring mechanism. And this is an interesting model because as a lot of network models, we can do a lot with pen and paper. We can get a lot of analytical intuition. And the picture we have in our heads is of a network that keeps rewiring like this, where people are trying to get away from the disease, rewiring away from sick individuals. That seems like a great idea in practice. In this paper, what you'll see is that behavior can have both like dramatic impact, but also unexpected impact, unexpected consequences. So I'll mostly focus your attention on the left slide here, which is this variation on the left panel, which is this variation in transmission rate, which we've already seen, and the size of the epidemic that we'd expect. So as we increase this gamma going from green to bluer colors, as we increase this rewiring rate, we increase the epidemic threshold, which is good. It's harder for a disease to invade the population, but eventually, not only do we get a discontinuous jump in epidemic size, but we also get larger epidemics when people are trying to move away from the disease. And that's because eventually the danger that you're putting the substitute nurse, the danger of infection that you add to the substitute nurse is not worth the decrease in danger to the healthy patient, essentially. And in terms of temporal patterns, what this means is that the epidemic or the exponential behavior that we've heard so much about doesn't hold anymore. You get this exponential behavior with a quick super exponential or acceleration rise before the peak. And that's a little worrisome, right? Because it shows us that we can add a little bit of what we believe to be realism, right? The idea that people don't like being connected to infectious individuals, they're just going to switch that. We think it should help. And not only does it completely change the basic insights we learned from classic epidemiological models, but it also means that we can't really trust potential forecasts because of these discontinuities. It's just so sensitive, right? So this is the type of thing that I think we need more of right now with the COVID outbreak. We ended up looking for this super exponential behavior in patterns of influenza. And we're not saying that this is the mechanism behind this, but the idea is that when you look at time series, you see really rich behavior, time series of real epidemics. You see a lot of rich behaviors, and classic models can't explain all of it. So we need really like all hands on deck right now trying to figure out what's the best way to make sense of epidemic data, which you're gonna hear a lot more about in the next tutorial. But yeah, so these models are completely solvable, and I think they're handy to like think about specific mechanisms. So here's an example of why I think it's relevant right now. This is a news from yesterday, right? I started preparing my slides yesterday, and I just went to like find what are people talking about right now with regards to the COVID-19 outbreak. And it turns out retired doctors want to return to work to fight COVID-19. Great idea. We need more healthcare workers. But these are people that are adding intentionally and for good reasons, adding SI edges in the system. So there's potential trade-offs here, right? And network models can help us think about these trade-offs and unexpected consequences, not to make better forecasts, but really to help us understand the role of mechanisms like these or decisions like these. So we turned one assumption into two. I said that already. Now we have this contact distribution approximated by some measure of heterogeneity. And then we had this pretty terrible assumption that infection status is not correlated with contacts, right? We know that if I have like 1,000 more contacts than you all, I'm 1,000 times more likely to get sick. That's why we're all at home right now. That's why we're social distancing. So infection status is correlated with number of contacts in real life, and we want to get rid of that. So even before those adaptive models, there were what I guess are better models in the sense that they include the pairwise models as special cases, and they allow us to consider the full range of heterogeneity, or the full range of a degree distribution. So another favorite of mine is this Epidemic Spreading in Scale-Free Networks paper by Pastor Sataras and Vespiani in 2001. Essentially, I'm not going to walk you through all the math, but now you're still putting people in boxes, depending on whether they're infectious or healthy. But the boxes are smaller essentially, because now you're going to put them in boxes depending on whether they're susceptible or infectious, but also based on their degree. Because you know that when you put people in boxes and write an equation for that box, you're assuming that all people in that box are going to follow the same dynamics. And we know that the number of contacts, the degree of an individual, governs their dynamics. So that's why now we want to have this transmission rate per contact and include this degree K in our equation. The big capital theta that's in our infection terms is just the probability that at the end of that edge is an infectious neighbor. So we can just like sum over all the links, count all the links in the network, count how many lead to infectious individual, and normalize that by all the links in the network. So this is what you have here. It's one equation, but it's a complete model. If you write and follow that equations for all degree classes, for all Ks, you have a complete model that allows you to show analytically that for very heterogeneous distribution, you have this vanishing epidemic threshold. So that's a really powerful approach. It's been generalized, and so this is the first paper I ever worked on when I started grad school. Generalized with what we call approximate master equations, where now you just the idea is we keep making smaller boxes. So now we distinguish people by whether they're susceptible or infectious, what is their degree, and how many infectious neighbors they have. And we're calling that approximate master equations because now you don't just have a binary state change, right, from susceptible to infectious. Your neighbors can change, and you have a lot more possible states for every single individuals. The math get a lot more complex, but you can show amazing things, localization of network dynamics around specific individuals. It's a really, really powerful approach. It's been formalized since. My favorite is formalization is by James Gleason in 2013. It's here on the screen. And we also, in 2010, considered similar approaches that didn't look at individuals themselves, but at connection. It's almost like an extension of the pairwise approach that we saw. And I'm putting here an archive. So it's a preprint that we released yesterday, but that looks at this generalization of the pair approximation. And basically what we do is we want to consider structures in a network, like events or schools, rock concerts, restaurants. And those things are not just pairwise interactions. They're cliques of highly connected individuals. And so far, we've only looked at random networks where specifying pairwise interactions is enough to specify the networks. And that's not good enough if you want to think about structural interventions that close schools or cancel events. So we generalize the pair approximation approach by looking at cliques and following the whole range of states that these cliques or events could take. And what that gives us is this phenomenon of mesoscopic localization. So I'll just point your attention here to panel A and B. Panel A is what you'd expect in a normal disease model, right? You can have larger cliques and you're just gonna have a higher prevalence as a function of the transmission rate in larger cliques because it's more contact. But it turns out that for very realistic, and I say that because larger exponents of a parallel distributions of this phenomenon that they don't have infinitely many like friends and all that. So I think it's more realistic. And when you're in that realistic regime where you don't have diverging averages, you get panel B. And in panel B, what we show is the black dotted line is as a function of transmission rate, the total prevalence of a disease, really, really low. But within specific structures like large schools of 100 people, you can have a very, very high prevalence. So early on, that helped us think about why closing school is such a good idea, right? And you saw people on Twitter and in the news saying, well, there's only like 5 cases in our country. Why does that matter? Well, those 5 cases happen preferentially in schools and restaurants. So that's why it matters to close those places. A disease in that is never uniformly distributed in a network, neither at the level of degree or in higher order structures like cliques and events and stuff like that. So this is brand new work. It's not peer reviewed, but I think there's a lot more research to be done in that area, thinking about higher order structures and temporal events and helping us think better about interventions and when we can relax interventions, and all of which are going to be critical questions going forward for the COVID outbreak. But the key part of these heterogeneous mean field models is that they allow us to relax these key assumptions. We don't have to rely on some simple metric of heterogeneity. and we don't have to assume that infection status is not correlated with number of contacts. So we get rid of that. We're just going to say that contacts follow some statistical distribution. It could be a degree distribution. It could be some higher order distribution of events and structures. So we're pretty close to the state of the art right now. I've like taken you from classic models to very, what I believe is state of the art differential equations to model disease on networks. And I'm going to switch gear completely and tackle the final assumption here, which is that the population is large enough to justify deterministic analysis. The idea behind that assumption is that if you have a lot of people, you could assume that the randomness of disease sort of cancels out, right? Maybe I didn't infect this person today, maybe I'll infect them tomorrow, cancels out on average. But early on in an outbreak, we know it's so important. You know, if patient 0 is someone without any contacts, it's very different than if patient 0 is a school teacher with a lot of contacts. And every single transmission event is just so random, right? If I'm closer to this person as they walk through a door, maybe I can just keep the door open and walk in. Whereas if I'm further behind, I have to touch the door handle, get the disease, right? There's so much randomness that goes into determining disease transmission that it seems at times a little ridiculous to think in deterministic terms. My favorite example is when we start forecasting emerging epidemics, right? So the start of the COVID outbreak, it's already about, you know, what is the final size going to be? How many people are going to get sick? And not in terms of what are the chances that this gets out of hand, that this becomes a pandemic, right? And we use like probabilistic forecasts and weather all the time, right? It's raining right now in Vermont, but even if I check the weather, they'll tell me, well, 80% chance in some areas, 90 in some other areas. So why don't we do that for disease forecast more, right? So I'll show you one network approach that helps us think in probabilistic terms. So this is a different approach, right? It's going to involve probability generating functions, completely different mathematics. For some of you, this might be new math. It's some of my favorite mathematical tricks. I'm very excited to show it to you. But I also know that it takes a long time to sort of get used to because it's very different from most mathematical models out there. So it's okay if you don't understand it. All the reference will be at the bottom, but I'll try and show you why I think it's so cool. So let's assume that we have degree distribution data. And that can come in practice from a lot of places. The first one here on the board is by educated guess, right? So we often say well, we know it's not a mass action phenomenon, so we're going to assume some heterogeneous distribution. That's what a lot of people do often because it's rare to get actual contact patterns. You could have some proximity data, right, from social media, cell phone, GPS, or people wearing little chips. That's out there. In practice for diseases, we often rely on contact tracing data. So that's literally data about who infected whom. So that comes from epidemiological detectives who go through and do the work of gathering that data. It's actually more of an intervention. The idea is that if someone comes in sick at the hospital, you want to send someone, you want to test their family or their workplace to try and stay ahead of the disease. But it gives us who infected whom networks, and that's super valuable for the modeling as well. It could also be viral genome sequences, the idea being that you can reconstruct transmission trees if you have good enough sampling, an idea of mutation rate, etc. It could just be analogies with past outbreak. You assume that this coronavirus is similar to past coronavirus. Or it could be fitting agent-based simulations to incidence data, keeping what makes sense, what looks like the data, and taking your contact patterns from there. It's a lot of different approaches. We describe them in more details in this preprint that's on the archive and medRxiv. There's a lot of references there to how people use these different approaches to try and infer contact patterns. So I'll just put this one reference, but it's work by other people that's really valuable here. Here's an example of contact tracing. This is also from a preprint that's on medRxiv. Maybe you can't see really well. So this is actual transmissions in China where edges and nodes are colored based on which province the transmission event occurred in. And as you can see, it's not a mass action, right? Mass action phenomenon, everyone would have mostly the same number of edges around them. But here you see that some individuals are just creating a lot more infections than others. So there are some super spreading events, is what we call them, around certain individuals. So we know there's heterogeneity, and we can use measures of heterogeneity or statistical distribution from data like these to inform our network models. How do we do that? Well, we never have good enough data to have a full transmission tree, right? So we never have a complete picture of who infected whom throughout an outbreak. So often what we'll do is create synthetic one, right? You can trust the distribution of secondary cases. So here edges mean actual transmission, right? So the degree distribution is, or the excess degree distribution is how many people am I going to infect if I get infected? And then you draw a number from this. I infect 3 people, and then I draw numbers from these. You infect no one, 2, 4, right? And you can generate random transmission trees. And the idea is that we would want mathematics that would allow us to consider and calculate all possible futures. What are the chances that this outbreak stops at patient 0? That this outbreak stops after 1 transmission, 2 transmission, 3, 4, 5? What are the chances it never ends and infects the entire planet, right? That's the idea. So the key part here is that we're going to change what we mean by network a little bit here. We could relax that, but I think it's easier to present the approach if we say that we're looking at transmission networks and not contact networks. So edges are contacts that would transmit if given the chance. And the average excess degree is now just this R0 quantity that we talked about earlier and that everyone talks about all the time, which is the average number of secondary infections caused by a case, right? A new case. And the next model I'm going to show is a network model. So instead of just looking at R0, it's going to consider the full distribution of secondary infections around R0, because we know it's not, a well-behaved Poisson distribution. There are super spreading events. Okay, so this new approach is probability generating functions. And the basic idea, if you've never seen them, is that these functions, they're just polynomials. Right, so a constant plus a constant times x plus a constant times x squared, and so on. But we're going to use the structure of the polynomial to store the probability of discrete stochastic events. So for example, we could have a probability generating function, which is just a data structure, where the coefficient in front of x time to the 0, so our constant, is just the probability of having no contact. The coefficient in terms of x, in front of x, is just the probability of having 1 contact. So here I'm just drawing the little network motifs that I'm talking about. And in front of x squared is the probability of having 2 contacts. So it's just the sum over my degree distribution pk of x times, of x to the kth power. There are like 2 really good reference here at the bottom. I also recommend, if you just want to learn more about probability generating functions, the book Generating Functionology by Wilf is just a classic in the field. Okay, so the reason why we use those data structure to store probability distributions is because it makes doing math with them a lot easier. So we might be interested, for example, in the PGF of a secondary infections of our patient 0. So now we're following an edge from patient 0 to someone else, and we want to know how many people is that person going to infect, right? So here I have the edge that we're following colored in red, and I can reach someone that's not going to infect anyone, someone that's going to infect 1 person, 2 people, 3 people, and so on and so forth. And here that's where we want to take into account the friendship paradox again, right? I know that I'm going to reach someone of degree k, k times more than I would reach someone of degree 1. So this G1 has to be a sum over this biased distribution kpk toward people with more contacts. And you can just normalize this kpk distribution, so it's easy to do the math. And now, obviously, there's a chance that this tree never ends. I do 1 step, I do 2 steps. If everyone infects 2 people, I infect 2, 4, 8, 16, and it just grows on forever. So that's how we can tackle this question of like, well, based on the distribution of secondary cases, what is the probability that we don't control this, that this gets out of hand? And here's a nice trick. We're going to calculate the opposite. We're going to calculate the probability that it does eventually stop, and that makes it much easier. So we're going to call that probability U, and we're going to say, well, U is the probability that I follow an edge, but that at the end of that edge is a finite number of nodes. I don't get out of control. I stop eventually. And I'm going to represent that by a square. It's a lot of nodes, but it's not infinite. All right, and that could be just 1 node. or there could be a node with 1 degree that doesn't lead to an infinite component, or there could be a node with 2 degrees that both don't lead to an infinite component, and so on and so forth. So really what I'm doing is just going over this G1 probability generating function again, but instead of just counting edges, I'm now counting U or U squared or U cubed at every term. And if I solve this U, so here I'm just solving a polynomial. It's like the same we've all done in math when we solve a quadratic equation, right? But what the solution to this polynomial gives us is the probability that an outbreak never stops, that it gets out of hand, right? And I'm going to call that R infinity. Or R infinity is going to be 1 minus that. So the probability that it gets out of hand. And that's pretty crazy because it's simple math. It looks very different from, I'm sure, a lot of what you've seen before. But it's just a polynomial that we're solving, and it gives us a very valuable probability. So a probabilistic forecast already. And here there's an interesting pattern because we're assuming, and we could relax that, but right now, the way I did the math, I assume that edges could be traversed in both ways, right? There's no direction. So if this edge exists, I would infect you or you would infect me. What this means is that you can imagine the entire population that you're concerned about. You put the edge across them, so everyone gets connected to people, and those are edges that would transmit. Now, when you infect a patient 0, every node that you can reach from that patient 0 is going to get sick, because that's what the edges mean. So then the probability that it never stops is the probability that your patient 0 is an infinite component, and that probability is also equal to the relative size of that infinite outbreak. What are the chances that patient 0 is in an infinite outbreak? So R infinity is both like a probability of things getting out of hand, but in terms of a fraction of our susceptible population, how many are going to get sick if it does? So it's both like a size forecast and a probability of that thing happening. Now, I won't go through this slide completely. I just wanted it to be up here for you all to see, but we can calculate the size of an outbreak if it does stop, right? If only one one transmission happens, nothing more, I get an outbreak of 2. If I infect 2 people, they don't infect anyone, I get an outbreak of 3. And calculating the size of all those trees. And you can see that we're just doing the same math, but now not asking for it to not be infinite, but just noticing that there's sort of a recursion going on, and we can define this distribution or PGF for the size of an outbreak in terms of itself. It's a lot harder to solve because it's not just finding the root of a polynomial, but if you do solve for this H1, U1, you can make a full probabilistic forecast. So what are the chances of an outbreak of size 1, 2, 3, 4, 5, and so on to infinity. So it's a really powerful framework. In our recent preprint, we also show if we assume a Poisson distribution, which is the mass action, we very easily fall back on Kerr-Mac-Meckendrick. So again, like this network model looks different, but it's not something that exists in a completely different universe. It's the generalization of the Kerr-Mac-Meckendrick analysis, which is useful to have if you know something about the heterogeneity. So we know we're grounded in classic results. And if we do have information about the full distribution of secondary cases, then we can use this. If we don't, maybe we're better off with Kerr-Mac-Meckendrick. Again, the idea is to not use stuff that you don't know in your model. But it's nice to have this hierarchy of potential analysis to leverage. The key difference is that R infinity is connected to Kerr-Mac-Meckendrick, but this model also tells us what might happen if the disease doesn't get out of hand. Right? So we get a full probabilistic forecast of different outbreak size. And to me, that's, that's the beauty of random networks and stochastic processes, but it's, when you use differential equations, you're saying like, give me everything that you know right now. So how many people are sick and transmission rates and all that, and it fixes like the future exactly. And when you see like forecasts in any of those differential equation models trying to predict the peak of the COVID outbreak, well, those error bars that it might put on there are just error bars about what we know now. It's not error bars about the randomness of disease transmission, right? It's just randomness of parameters and initial conditions that create a randomness in the forecast. Here it's something different. You can have randomness in your parameters, but you also have randomness in the process itself. So I think it's just a much more powerful approach, and an approach that's just much more cognizant of the complexity of actual disease transmission. So these are the only like fresh results I'm going to show with this approach. The idea is like, what does it mean for COVID-19, right? So very early on in late January, I think, when we started getting numbers about both R naught, you probably remember people debating whether R naught was 1.5 or 2.5 or 3.5. But people were also estimating this dispersion parameter, which is a misnomer a little bit. A high dispersion parameter means low variance. So a more homogeneous degree distribution or secondary case distribution. And here what I'm plotting is a contour plot. So it's like a heat map, but I like these better because I get to show the number. I'm not good at comparing colors. It's a heat map of the R infinity, so the final outbreak size, or the probability of COVID getting out of hand based on these early data, as I vary R naught on the x-axis and this dispersion parameter or the variance on the y-axis. And back then in January, our estimates was that there was between a 10 and 50% chance of things getting out of hand with COVID. And the interesting part here is that things get out of hand more easily if you have a low variance. And actually, if you have a high R naught around 3, the dispersion parameter or the variance around R naught is actually more important than R naught itself, right? So low variance means everyone infects 3 people. Obviously, it's going to get out of hand if everyone infects 3 people. High variance means that you have some super spreading events somewhere waiting to happen. And then it's much more easily to control that disease, because if you manage to stop that super spreading, that event from happening, whether that's a church meeting or spring break or whatever it is, if you stop that event from happening, then you've controlled your outbreak. So diseases with the same R naught but higher variance are much easier to control. And that's why I think when we debate around emerging epidemics, it's really important to not just think about R1. R1 is great. It's an average, it's a number, easy to understand. If it's greater than 1, okay, we need to look at this more carefully. But it doesn't matter that much whether it's 2.5 or 3.5. We want to know how much heterogeneity there is behind it. Because a lot of heterogeneity means that it's more easy to control. If we can stop high spreading event, super spreading event, we might be able to win. Now, obviously, the more numbers come out, it looks like this is actually a lower heterogeneity, lower variance, and therefore harder to control, obviously, outbreak. But this is, I think, very useful to get the big picture or the complete picture around emerging epidemics. Since then, we took the time to look at other diseases, because a lot of these approaches have never been validated. Real disease modeling is so noisy. Here I'm just comparing almost for fun, but it's reported cases in different communities of different outbreaks from 1918, so the influenza pandemic of 1918. And I show with X markers, right, the proportion of susceptible individuals in that population that were infected. And then I compare the Kermack-McKendrick model in red. So it's a deterministic model, but the error bar on here represent the confidence interval that we have on R naught. And our model, the network model, in blue, where the most likely value is the blue square, but the range here considers both R naught, heterogeneity, and the stochastic process behind disease transmission. And in general, you just, I think, get a much better picture of what could happen if you consider this stochastic process rather than deterministic SIR. Okay, so we tackled this last assumption. Right? I know it's a model that's new to a lot of people, but it shows the power of network thinking and random processes. So now we don't have to assume a deterministic analysis. We don't have to assume that disease transmission is super well behaved. We can embrace the complexity. We're still assuming that the population is large enough. And I think that's just part of the type of things we're trying to model here. We're never going to ask, oh, the disease just entered this household, how many people are going to get sick? That would be like completely different type of models. Here we're concerned with large population and not individuals themselves. So we're still assuming a large population. In fact, the math I showed is exact in the limit of an infinite population. But I think that's just not something we're going to tackle with these types of approaches. So the last thing I want to talk about, and it's not to relax this last assumption, is just a different framework, which I think is I believe to be the state of the art of a lot of the COVID modeling happening right now. But I want to show that what I discussed today is very, very close to what you're seeing in the news. So, and of course in the news, you see a lot of also bad models that are worse than classic SIS and SIR or what I've shown. But there are people out there that have made their own expertise of modeling disease really, really well. And here's my favorite example. So it's the team at Northeastern on the GLEAM project led by Alessandro Vespignani. And I invite you to go look at their website, gleamproject.org, or at their recent paper in Science, which you might look at it and think that this is out of reach for you if you're new to disease modeling. It's actually not that complicated, right? So the approach that they use is what we call the meta population framework, where you have a network around locations. So you define, a few thousand locations around the globe, which are places around a travel hub. And then you can define connections across these travel hubs, these locations, by how many people take a plane from location A to B, how many people take a train from location A to B, and you can define edges. And within these subpopulations, then you're just going to use your favorite disease propagation model. So it could be a network model, it could be classic SIR. Of course, in the case of COVID, they don't just use classic SIR, they add an extra state between S and I to account for the fact that maybe you have pre-symptomatic individuals that are still transmitting the disease but not testing. But you can use your favorite model that I just showed within those populations and just couple them if you have enough data to do so, right? And data is really the part that drives a lot of these state-of-the-art models. The very last thing I'll say before I wrap up is that if you're interested in doing your own simulations or solving ODE models and you haven't played a lot with ODE Solver before, I just really can't recommend this enough. It's the Epidemics on Networks package that's curated by Joel Miller and colleagues. So it's available for free online. It's a fast Python package that does both simulation and solving classic models. But it's built over the Network X package for Python. So all the network stuff that you might know from Network X can be applied in here. And then it's easy to implement your own model or run different things. So it's available for free online. And if you want to do your own simulations without having how to learn really complex simulation, I think this is easily the best option out there. It's also based, all the algorithms and all the models that they've implemented are described in this textbook. It covers almost everything that I talked about and then much more. So if you want a more complete overview of network models for diseases, I really recommend this textbook. And then I'll share my slides if the organizers haven't done so already, so that you can have all the reference that I talked about and sort of see the evolution of these models through time. With that said, I'm almost on the hour, so I'm pretty happy about this. So I have to thank whoever, all the people and organizations that supported this work. The work I talked about, I've been doing for a long time. So it started at the Santa Fe Institute and the Institute for Disease Modeling, now at the Complex STEM Center and our new Tiger Centers for Infectious Disease at Vermont. But with that, I think I'll try, this is my first Zoom talk, but I'll try to take as many questions as you might have. So thank you very much. Should I curate my own by looking at the chat, or how do we do this? Oh, I'm the host now. Oh, I'm sorry for just waiting. I will put someone else as host. Juniper, I think you're unmuted and now host. If you want to make Michelle host, or it's out of my hand. I can start answering questions though, if that's all right.
Okay, please start answering questions. And also some of our co-hosts will go through and pick out some questions for you. But Laurent, take it away since you have the chat window as well.
Okay, I see people are answering questions on their own too, so that's pretty amazing. I was gonna say exactly what Nicholas Roberts just said. So this average KX quantity, the average excess degree is not something about triplets or pairs. It's really just the expected number of other friends that your friends might have. It's just very different in a network. When you follow an edge, that person is likely to have a lot of other friends other than you. So it's not something about pairs and triplets. It's really a property of the individual degree distribution. And I see a good question here from Benjamin. In your network models, do you distinguish between a clique of contacts that happen in distinguishable pairs versus simultaneous interactions? So the way I understand this is like, in these models, let's say is there a difference between a triangle that occurs because it's a triangle, so like a family unit, versus 3 pairwise interactions that just happen to form a triangle? And most of what I've shown, because we assume a very large population, 3 random pairwise interactions are just never going to happen to form a triangle. It's just very unlikely. In fact, the math assumes infinite population, so it's just not going to happen. In finite simulations, though, that could happen. And in classic models, classic disease models, we don't distinguish between a triangle that happens by chance versus a family unit. There's a new line of work of dynamics on higher order networks or hypergraphs or simplicial complexes that does look at the fact that, well, maybe a real triangle is different from 3 pairwise interactions. So there's new line of work. I'd invite you to look at recent work by Giovanni Petri and a lot of others if you want to look at that. For disease models, often we don't really need that. In a lot of ways, we think the total number of exposures is all that matters.
All right, here's a good one here. I think that many people would like is to go back to the slide with the heterogeneous networks. What was the pink star network in the center?
The pink star. Oh, yeah, what I showed of
Yeah, the pretty one, the real data. Yeah. This was. Yeah.
I'm trying to read what. So at the very bottom of the plot, you have. I mean, and I think we shared the slides, so someone might be able to see that easily. At the bottom of the plot, you have the color code. So the color here means which province this transmission occurred in, and I'm trying to read what the pink province on the right is, but I can't quite make it out. So like black, for example, is Hong Kong, red is Beijing. I'm not sure what the pink one is, but it's a particular province that just happened to have a super spreading event.
I think it says Beijing. Is that the one, or is that the wrong color? No, that's red is Beijing.
Yeah, it's red. Pink is like the third one from the right, and I just can't.
Oh, maybe it's Wuhan? No, I can't tell.
No, I think they removed, this is excluding sort of the larger, more affected provinces. I'd have to look at the paper or zoom in on this, but I can't right now.
And
Tianjin, I think that's right. Someone said it. Daniel Citron, Dan said it. Tianjin.
Yeah. Let's take one more question, and maybe we could even continue some of this later, Laurent, if you have some time to answer questions on our Slack site, if you want to pop in there. I'll
be available for the next weeks.
Okay, well, excellent. So there was another question about going back to the high-low R naught and the high-low variance slide. And I think there was a little bit of a misunderstanding that high-low variance goes with low-high R naught, but can you just explain this graph again?
Yeah. So really you can have diseases can go in 4 directions, right? You can have low R naught, which would be closer to R naught of 1, with either a low variance, so that's like everyone infects 1% or maybe 2 people, but no one infects 3. Or you can have a low R naught with a high variance. So that's something like Ebola, right? Or you might have an R naught of 1.5, but 85% of your cases don't infect anyone. And really it's driven by super spreading event. So right now that would be the left of this plot, and Ebola would be on the bottom left, and something like a very weak flu might be at the top left. So obviously if your R naught is very low, you need a low variance to be able to spread. Whereas on the right side of the plot, you have just really strong R naughts. So something like measles would be, outside of my apartment. But let's say you have an R naught of 5. Once you're in those high R naught ranges, really all that matters is your dispersion. So how much variance you have. So that's why if we think that COVID is strong enough to be like close to 4, as a lot of people did early on, then it really matters whether it's high variance or low variance. And high variance means driven by super spreading events, so easier to manage. whereas low variance means just everyone infects 4 people, and that's like worst case scenario, obviously. So that's sort of the entire range of possible outbreaks. And again, these distributions, both R0 and the dispersion parameters, are not just a property. I keep like implying that they're property of the diseases itself, they're property of the pathogen and the population and the intervention, the context. So there's a lot that goes in those 2 numbers, but really together, they really shape the potential futures.
Excellent. Thank you, Laurent. If we, I don't know if participants in our settings can do their reactions, but if we could all do a round of virtual applause. That was a great seminar to start us off. We're very excited about it all. I am trying to share with you we're asking you to, if you have a chance, to go to our feedback form. go.umd.edu/netcovid_1A for this session for feedback. I've just put it in the chat form. So thank you. This was a great first session. Thanks to everyone for attending. I've loved that you've been answering each other's questions in the chat window. Thanks especially to Laurent for kicking us off with this really informative tutorial. We are going to sign off from this tutorial. We'll start up the next session soon. That room will open, but we're going to take a 5-minute break. So we'll really start it at 1:25, the discussion section. So for those of you who are part of that series, you have a separate link in your email for that. Thanks so much, and we look forward to seeing you back next week.